So before we start this section or the discussion of how to do the substitution method, I want to remind you what an indefinite integral looks like. And we've been discussing in class some definite integrals, like the definite integral from a to b of the function f of x with respect to x. Now this definite integral has limits of integration. We can use the fundamental theorem of calculus to crank this into a number, and that number represents the area under the curve. Indefinite integrals are what we saw in section 4.8, just the integral sign of the function f of x dx. This thing is asking us to find the antiderivative of the function f of x. So what we got back was the antiderivative capital F of x plus some constant c. To illustrate this for you with an example, we could do the indefinite integral of the function 2x with respect to x. Say the antiderivative of 2x is x squared plus any constant c for the family of functions that satisfies this indefinite integral. But if we did the definite integral, we'd have lower and upper limits, like 1 to 3 of the function 2x with respect to x. We'd find the antiderivative x squared, evaluate it from 1 to 3, and find out that the value of this definite integral was 7, the area under the curve above the x-axis between 1 and 3. So what we're doing today in this video is finding the most general antiderivatives with a little bit more advanced technique. So look at this integrand. It's a hot mess, right? We have this x cubed plus 4x to the 4 times 3x squared plus 4. We cannot just integrate this thing as like, oh, let me find the indefinite integral of this and then multiply by the antiderivative of that, because it won't work. Like the way that these functions are related with multiplication, if we were to differentiate from there, we wouldn't get the same value, which is the property, the main thing that determines we have the correct antiderivative. So another way to think about this function is perhaps we need to make a substitution that can let us see what's going on here, maybe simplify what we have. One very valuable method for computing integrals like this is to make a substitution that will reduce the integral to something that's easy to find the antiderivative of. Let me usually choose the variable u, represent something kind of complicated in the function, and by complicated I mean the thing that makes us think we have a chain rule. So in this example, what if I took the inside of the stuff that gets raised to the 4th power, x cubed plus 4x. This thing has its own derivative, we'll call that du, and the derivative of u is 3x squared plus 4 with respect to x. Then when we re-examine our integrand, we can make the substitution. So like I said, this part x cubed plus 4x is u, and then lo and behold, this extra junk out here, the 3x squared plus 4 dx, is the derivative of u. That transforms the integrand to the indefinite integral of u, still to the 4th power. See, we still have this exponent, but then just times du, or with a change of variable to du. So now that we have a simplified integrand, we can simply integrate it, find the antiderivative. So take u, it was to the 4, go up 1 power and divide by that sum. So that's u to the 5 divided by 5. But then recognize that our variable has switched. We started with x's, we need to return to x land. We turned into u land to make an easier integrand. We did the antiderivative. Now let's go back and see what happens when we replace x for u. So still this stuff is to the 5th. We still divide by 5. But the bridge between u and x is this. So we had u to the 5th. We replace the stuff with x in there. And then we can add c. So I would simplify this as 1/5 x cubed plus 4x to the 5th plus c as the correct antiderivative. Of course, we can check that antiderivative. We could check it by taking the derivative of it to see if we get the integrand. What's the derivative with respect to x of this antiderivative? 1/5 x cubed plus 4x to the 5th plus c. If we take the derivative of this thing that we cover up, we get chain rule, right? 5 times 1/5 x cubed plus 4x to the 4th power by the derivative, and then by the chain rule the derivative of this, which is 3x squared plus 4. We can clean that derivative up. The 5's cancel, and we get x cubed plus 4x to the 4th times 3x squared plus 4. So lo and behold, the integrand matches what we tried to do in the beginning. This method is called u substitution because we typically use the variable u to make the substitution, and it's one of the most valuable things you'll learn when trying to find antiderivatives of more complicated functions. So unfortunately, the best way to do it is just do it and do it and do it again and keep practicing and trying different kinds to find what good substitutions are and get used to changing the variable to something that makes the problem easier. So that's going to be our approach here. Just keep practicing. For example, here's another function. I don't know what the antiderivative of this thing is. So let's let u be the inside of the radical, 7x minus 1. Then the derivative of u is the derivative of this 7x minus 1 business, which is 7 with respect to x. So in our integrand, I have this stuff underneath the radical as u, and then 7 and dx together make du. Therefore, the integral reduces to the square root of u times du, or with respect to u. We've reduced the integrand. There are only u's there. Now we can find the antiderivative of this. You might still need to say, okay, this is the integral of u to the 1/2 with respect to u. So to find the antiderivative, we'll take u to the 1/2, add 1, and divide by 1/2 plus 1. That's how we get the antiderivative. U to the 1/2 plus 1 is u to the 3/2. And dividing by 1/2 plus 1, or dividing by 3/2, is the same thing as multiplying by 2/3. Then you say, oh geez, we need to return to x land. We turned into u land, we got out of the integral, we did most of the work, but we have to return, go back. Our problem was in x, we need to give it back into x. So this is 2/3 times the stuff with x to the 3/2, and the stuff with x was 7x minus 1, and of course we add c because this is the general antiderivative of the function. So there we found, with u substitution, the indefinite integral. Now the steps for this we can outline, but they won't become easy until we've done a lot of practice. First, we need to decide on u. What is a good u? Ways to pick u. They'll be inside parentheses, maybe under a square root, or some kind of radical. Denominators make good u's. Pretty much anything that would make you think, I am going to need chain rule if I differentiate this. Once we determine what the u substitution will be, we want to find du. What is the derivative of that expression? So find du, simple differentiation of the u we've selected. Then use this u and du to rewrite the integral. In terms of u and du. We need to make sure it's a total change, completely 100% into u and du. We can't have some extra x's or t's or y's floating around. We need just one variable. Once we've made that transformation, we can find the antiderivative with respect to u. And then now we know the antiderivative, we can return to the original variable. So like I said, the hardest part of this is determining a good substitution. What should we make that's going to simplify the integrand? And we'll do a lot of examples, and I'll show you a lot of things, and you'll practice, and you'll make the wrong choice sometimes, and then you'll go back and say, that didn't make it easier for me, let me try it again. There's no harm in that, no shame, just to try a different u until you can simplify the integrand to something that we can find the antiderivative for. That is the goal.